Any questions on the homework for today? Okay. All right. So figure 1146A. Easier to pick this up. Question asks, if the transconductance is 3,000 microsiemens, what is the stage input impedance and the AC output voltage? So you need those values. Okay. So the input impedance for our JFET amplifier is approximated as R1 in parallel with R2. But the input impedance of the transistor itself is so high. So 20 in parallel with 10 gives you about 6.67 mega ohms. Now, the output voltage will be whatever the input voltage is times voltage gain. For this amplifier, the voltage gain is given as the transconductance times the AC drain resistance. The AC drain resistance is the collector resistor, sorry, not the collector, the drain resistor in parallel with the load resistor. We have 1K and a 10K. That gives me basically 0.0909 kiloohms. And then the voltage gain would be 3,000 microsiemens, which is also 3 millisiemens, times 0.909 kiloohms. So that's a gain of 2.727. And then our input, 2 millivolts. And we have a 10K generator resistance, but with an input impedance of 6.67 mega ohms, everything is there. So basically, the output voltage then would be the 2 millivolts times our gain of 2.727 or 5.454 millivolts. Any other questions on the homework? 20. 20? All right, so this is figure 45B. Bias resistors. Six for 7. Oh, there it is. Oh. All right. 45B. Right? There was Number 20, 45B. Okay. All right. 45B is this one. All right. So we've got 25 volts. And 1K. All right. 1.5 meg per G. Yeah, I'm not going to worry about that. It's not going to matter. All right, the voltage across to 1K is 1.5 volt. So we are basically given a voltage, 1.5 volts, across the 1K resistor. So Ohm's law says that then the current would be 1.5 volts divided by 1K, 1.5 milliamps. Now, technically, that's the source current, but that is also the drain current. Now I have 1.5 milliamps flowing through 8.2K. That'll produce a voltage drop of 12.3 volts. And so the drain voltage, which is what the question was asking for, would be 25 minus 12.3, or 12.7 volts. Okay. Any other questions? Okay. Well, we do have a few more things to talk about in chapter 20. I'm sorry, chapter 11, question number 20. And there are several things to go through. I don't know if I'm going to draw all of them, but I'll kind of run through it a little bit anyway. So multiplexing, everybody in here has had digital, so we're familiar with digital multiplexing, where we take multiple digital signals and bring them into a single path. Well, we can use JFETs to do the same thing. So if I have, signal A, signal B, and signal C coming in, what I can basically do is just put a JFET here for each signal. Combine them together, essentially provide an output. Because what I can do, right, remember, if we bias the JFETs into the ohmic region, then what they are doing is serving as essentially a conduit for the signal to go through and be developed across, usually call it RD, I think, in the book. Let's see. Yeah, RD. So all I have to do is apply say negative 10 volts here, negative 10 volts here, and 0 volts here. And now C goes through. Because by putting a negative voltage onto the gates of those JFETs, they act like opens. So I'm basically using each individual JFET as a switch. It allows me to take whatever signal I want to go through. And this allows me to switch analog signals, not just digital. One simple use. We can also use a a JFET in a similar manner. So if I basically just use my JFET to take a signal, turn it on and off. So I'll just say 10's a nice voltage, right? So if I'm just going between 0 and minus 10 volts, I'm taking this JFET and turning it on and off. So what that allows me to do then is basically create a chopper. So if this is a DC signal, right? So it's got a constant voltage, an input voltage. Well, now by turning that signal on and off, what I end up with over here is either the input voltage or 0. Now have essentially created a square wave, which I can then amplify. So now we run this into an amplifier. Now the output is bigger, right? 0 to whatever the input voltage is times my voltage gain. And now if I run this into a peak detector, I'm basically taking the peak, which is now the input voltage times the voltage gain as my output. So what this is effectively is, it's a DC amplifier. I'm taking the DC voltage coming in, turning it into AC that I can amplify, and then taking the new peak as my output. VN. VN is just a DC voltage. I added a DC here. And so this is actually one of the options you have for your lab. Because let's say, for example, this is a very slowly changing voltage. So maybe this looks, like a very low frequency amplitude sine wave, which, as we're going to learn in a couple of weeks, it's hard to amplify low frequency with some of our amplifiers because of our coupling. Well, now I chop it up. So now, instead of having a sine wave, I end up with this, etc. Okay. Well, I'll still amplify this into that. And now, as I make this bigger, it has the same shape. My peak detector will basically kind of give me back that amplified sine wave. So by basically chopping this up at a higher frequency, I can use my standard amplifiers to go ahead and amplify. Use a JFET amplifier as a buffer amplifier because one of the things we learned about it has a very high input impedance and can have a relatively low output impedance. Very similar to what we did with our bipolar junction transistor amplifiers, where different configurations provide a different amount of input and output impedances. The JFET is also good for low noise applications. One of the things about bipolar junction transistors is because we have a forward biased PN junction, when holes and electrons recombine, which is what's happening when they're forward biased, that actually creates some amount of noise. A JFET amplifier has no forward bias junction, right? The gate is actually reverse biased. So you don't have that recombination noise happening in a JFET. So very useful for me there. Oh, here's another option you have for your lab today, or not today, but that you'll get assigned today. A voltage variable resistance. In some ways, that's going to be, I don't want to call it a focus, but it's one thing that is going to come up as we go through this course sometimes is the ability to convert a voltage into a current or a current into a voltage using one input to control what happens on the output. So the JFET can be used as a voltage controlled resistant. So if you remember, when we did our curves last week for our JFET, we had our drain current versus our drain source voltage, I think. Yeah, yes. And so we had these curves that we created. For example. Well, if we focus in on this part right there, what we find is that's your gate source voltage at 0. But if I do a gate source voltage -1, or gate source voltage of -2, or gate source voltage of -3, right? Just to give you some examples here. Well, all of these originate at 0. And because this is, oops, I'm sorry, voltage. And because this is current divided by voltage, the slope of this line is proportional to 1 over the resistance between the drain and the source. Now, when we calculated our RDS last week, the focus was on this curve only. And we said, well, when you get to the pinch-off voltage right here, that is IDSS right there, that is the drain source resistance of the transistor. But that's only when the gate source voltage is 0. When the gate source voltage becomes more negative, the slope goes down, which means the resistance is getting larger. So each of these different voltages can basically vary actual drain source resistance. So a voltage controlled resistance. We are quite literally using an input voltage to change resistance. You know, we're used to having to do what to change resistance, right? All our potentiometers, you got to grab a knob and turn it. That's a physical input. Now I have the ability to use an actual voltage to change it. You know what? Did I skip? I skipped a whole section on switch. Yeah, I'll go back and get that. I'm like, why haven't we talked about the switch yet? Oh, it's because I missed that part. Okay. Now you can combine this then. All right. So once you have this concept, we can just go ahead and, for example, put the JFET in here like this. So I have an input and I have an output voltage. And then by varying this resistance, this is just a voltage divider. And by varying the resistance of the transistor, I can vary the output voltage. I can vary the effect of this voltage divider by controlling an input voltage. You can use that, as a voltage control. You could do it in series or you can do it in parallel, whichever one you want to do. I'm sorry, not series. Well, you can either take it across the transistor or you could reverse it and take it across resistance. This is actually, so this configuration that we have right here, this is actually the configuration for a switch as well. Okay, but with a switch, what am I doing with the transistor? Turning it on or off? I turn it as on as it can be, or I turn it off. We'll come back to that here in just a second to go through that. So I can use this type of configuration with the variable resistance as a control of the size of a signal into an amplifier. And by varying and by taking some feedback from the output of the amplifier circuit, I can vary the size of the input, and that is another form of automatic gain control, AGC. Like I said, I'm not going to draw all these things up. It's sometimes fun just to talk about it. I can use it for current limiting, right? Because remember that when I have my JFET set up, we go back to here, there's an automatic current limit that's going to happen that will limit the current. So I can operate somewhere where I'm maybe controlling the amount of current, but in the event of something, say the load shorts out or anything like that, that's your maximum current. Done. Stuck there, whatever it happens. All right, so a few other options like that. But let's go ahead and backtrack here to my analog switch, right? So I kind of started off over there by using the JFET as a switch to multiplex, but I never really covered it as a switch. But we'll do that right here. So right here, I'm basically going to operate this switch with either 0 volts or, again, we'll just say a negative V, right? So this transistor will be on or off. Now, this is referred to as a shunt switch because I'm taking the output in parallel with the active device, right? Everybody had power supplies. Those words should sound familiar. Well, that makes this a series switch because the active device is in series with the signal. But for my shunt device, do the same thing here, right? So now it'll be minus V and 0. We'll see the difference here. So for this device, when I have 0 volts input, this is on. And this is going to act like RDS. Now, under those conditions, so in the shunt configuration, when the gate source voltage is 0, the switch is off. And here's why. The output voltage, the voltage divider, will be whatever the input voltage is times RDS divided by RDS plus the drain resistor. Well, RDS is relatively small compared to the drain resistor, then this output voltage is going to be very small. Make sense to everyone? Now, for the series configuration, when the gate source voltage is minus V, minus V, in other words, very negative, that is also my off. But in that case, if the transistor is off and this basically acts like an open, then the output voltage will be 0. For my shunt, when the gate source voltage is negative V, that is on. So with the negative voltage into the gate, this transistor is off, and it acts like an open, which basically means the output equals the input. For the series configuration, the gate source voltage is 0, that is my on. Well, in that case, this acts like RDS. And so I have a voltage divider where now the output voltage will be equal to the input voltage times the drain resistance divided by the drain resistance plus RDS. And once again, that drain resistance is a lot bigger than RDS, then this fraction is very, very close to 1. Now, the other way to evaluate a switch, all right, is to say, all right, what is the ratio between the output voltage when it's on and the output voltage when it's off? A true switch would be what? When the switch is on, you get everything. When the switch is off, you get nothing. So that's an infinite ratio, right? Whatever the voltage out is divided by 0, or technically voltage in. So for my series switch, that's exactly what I get, right? The output voltage is really close to the input voltage when it's on. Oh, yeah, on. But then when it's off, the output is 0. So that's an infinite ratio. Here, when the switch is on, I get all of the input voltage. But when it's off, I get a small fraction of it. So when you do that ratio, V in cancels out, we take the inverse of that. And that ratio will be fairly large. All right, let's say that if we just say that the drain resistor is 100 times bigger than RDS, then that's a ratio of 100, which is pretty good. Nowhere near infinite, but take what you get. All right, so that is my JFET analog switch. You'll have a couple homework problems on that. And then all those other configurations, those will be options for your lab. And that is my completion of chapter 11. Any questions on JFETs? Moving on, chapter 12. So I'm going to start our discussion of chapter 12 with what is known as a depletion mode MOSFET. So we're going to kind of start in a very similar manner to what we did with our JFET. So we have a block of N-type material, and then I kind of add in some P-type material right here. That P-type material is just connected to ground. So that's going to be my ground here. And then we'll go ahead and connect over here as well. So here's my source, and here's my drain. And then we'll go ahead and put a positive voltage on the drain with respect to the source and this material. So we start off with this channel. So we have a channel set up. Now, here's where it's different. So instead of creating a PN junction, we're going to take the semiconductor material and we're going to basically coat it with an insulator. This is actually done fairly easily by exposing silicon to oxygen and oxidizing the silicon, because that creates essentially silicon dioxide, which is what? glass.
Oh.
It's essentially sand, but when you melt it, it's like glass, right? So glass is an insulator, so that's very easily done. Then, on top of that insulator, I put a conductive metal coating, which essentially acts like an electrode or just a sheet, if you will. And that is my gate. So there is no junction. Kind of like we started before, we'll go ahead and connect that gate to ground. We're once again looking at our drain current. So I have a drain supply voltage here that I'm going to change the value of versus the drain to source voltage. Very similarly to my JFET, as I increase that drain to source voltage, we actually end up pinching off a channel. So we do have a channel for current flow here, right? The electrons can move, okay? And as the voltage gets up higher here relative to the ground, then I end up pinching off the channel, and I basically create a very similar curve. Here's what happens. If I make this gate voltage negative, gate supply voltage there, if I make the gate negative, before I start to increase this voltage, what have I actually done? This is a conductive material, another conductive material, separated by an insulator. What is that? It's essentially a capacitance. And so if I put a negative voltage on this side of the capacitor, what happens on the other side of the capacitor?
I think that
We get a positive charge. Well, the other side of this gate is N-type material. So if I bring in positive charges, I'm essentially saying, hey, you know those free electrons? Bye-bye. And what we actually kind of end up doing is creating a region here that no longer has my free electrons. What does that do to the size of this channel? It narrows it. Just like my JFET, with the negative voltage on the gate, that channel is smaller and therefore higher resistance and pinches off sooner. So I essentially get the same result that I had last week in terms of what these curves look like. To the point where I could, with enough negative voltage, cut off that channel. Now, here's what is different than the JFET. If I reverse the polarity of the gate voltage, now what happens? So if the gate is now positive, that means the other side of my capacitor is going to have negative charges. In other words, I'm going to bring in more electrons. Well, that makes the channel what? More conductive. And so I actually create another set of curves when the gate source voltage is positive. So this is known as a depletion mode metal oxide semiconductor field effect transistor. Or in short, a D mode MOSFET. Sense to everyone? Down here, depletion mode. Up here, enhancement mode. I'm adding to that conductivity of that channel. Now, we're not going to spend a lot of time on this, because that's not what our focus is going to be. This is not the ones that are used a lot. It's kind of neat, right? You get that additional flexibility. You can use this like a JFET in a lot of ways. But what I'm going to do instead is I'm going to build this a little bit differently and basically take away the initial channel. Well, this is going to operate very similar to my JFET. I have we have a formula for that, okay, where you have your drain current is your IDSS, right? So our IDSS still exists here, right? When the gate source voltage is 0. But this formula still applies. The difference is when we draw our curve, so if I look at the gate source voltage and the drain current that results, so at 0, I have basically this point right here, okay, that's your IDSS. When I get enough negative here, the gate source voltage is low enough, I end up at cutoff. The difference is that curve keeps going. That curve keeps going. So if I actually, for example, I have 1 volt here, and I divide by that gate source cutoff voltage, so now that's a negative. Minus a minus becomes a plus. This now becomes greater than 1. And when I square it, I keep going. That's the difference. With the JFET, we don't want to put a positive voltage on it because now it's no longer a reverse bias junction. So again, this is our D mode MOSFET.
Seems like you could push that too far.
You could.
Our current to bias.
Yeah. Well, I mean, when we build it, I didn't put any resistors in there, but always, if that possibility exists, you want resistors to limit that current. Now,
This had the same low noise characteristic.
Yeah.
It must.
yeah, because I have no forward bias junction. That is, it's the forward bias PN junction and the recombination of holes and of free electrons that makes that noise.
Is this any better or worse as a low noise amplifying device?
Than a JFET?
Yeah.
I'd say they're probably comparable.
But this is more expensive.
JFETs are pretty easy. But here's the way that we're really going to work on it. We start with the same concept, same idea here. But instead of leaving a channel, now there is no channel to begin with. Still built the same way. Let's take an outside layer. I put some metal on the top of it for my gate. Well, now only going to use a positive gate voltage. And when this gate voltage is initially 0, there is no channel. There is no current. With a positive voltage on essentially this side of my capacitor, I will draw in electrons. When this voltage is high enough, there will be enough electrons here to fill in the holes and eventually have enough electrons to create a channel. So there's basically, he describes that as something inversion layer, I think. Can't remember the word here. N-type inversion layer. I knew it. Something there. Remember, N-type means what? If I say something is an N-type, that means that it has free electrons as its main carrier. So once the voltage on the gate is positive enough, and I pull in enough electrons on the other side of the capacitance, then the holes are filled in. I have enough of the excess electrons to create effectively an N-type material. And now I have N connected to N, and I have current. Make sense to everyone? So in terms of what that picture looks like, when we look at the amount of drain current that we get versus the drain source voltage, initially, I got nothing. But at some threshold gate source voltage, I just start to see current. If I increase the gate source voltage, make that inversion layer bigger, more conductive. Say 5 volts. Make it 10 volts, make it even bigger, even more conductive. So I create the same family of curves for varying gate source voltage once I reach that threshold. We look at the curve, what we call our transconductance curve with our JFET, and kind of did the same thing over there. If we look at the amount of drain current that we essentially saturate at versus the gate source voltage, this is still a square law device. You still get that shape of curve. It's shifted over. Point at which the current begins to flow, again, that is my gate source threshold voltage. Once I get beyond that, I have my square law. Now, similar to what Larry asked about earlier, it's like, could that be taken too far? If I just keep increasing the gate source voltage, that threshold current gets higher and higher. This curve just keeps going up. But, and what I said earlier was, well, we're going to probably have a resistor to limit that current. Well, what happens when that current ends up getting limited? In our bipolar junction transistor, we call that saturation. When that current gets limited by external resistors in a JFET, we call it the ohmic region. Same thing happens here. So what is assumed at some point is that we reach a point where the current is limited not by the transistor, but by an external resistor. And so this is our drain saturation current. So now this is my active region. This, my ohmic region. Just like any device here, we're not going to redraw it every time. We have schematic symbols for these. For my, oh, and by the way, because this has no depletion mode, this is called an enhancement mode. Our schematic symbol for that basically looks like here's your gate, drain, source. Now, this is an N channel. You do this whole thing by reversing everything. P and P. Now, what voltage would I need on the gate to create a P channel? In order to create and draw in holes on the other side of my capacitance, I would need a negative voltage on the gate. So the N channel enhancement mode MOSFET requires a positive gate voltage to work. The difference between the two is just which way that arrow is pointing. So when the arrow is pointing out, that's a P channel. Enhancement mode MOSFET. The difference in the schematic symbol between enhancement mode and depletion mode MOSFET is right here. See how there's a break between there? This is E mode. The depletion mode no break. This channel is already there for us. There's already a path to flow. Here, no path until I create one. That's the difference in the schematic symbol. Of course, for my P channel, then what I need to be able to do is basically use a negative voltage on that gate to create the channel. So very similar, and I don't even know if he does much with the active region here. I don't think he does. Let's see. Yeah, not so much. So just so you understand, you do have the ability. You bias this transistor into the active region. You operate in this area here where your gate source voltage is controlling the amount of drain current, you do have the ability to build an amplifier with this. But more often, this device is used as a switch. And for that purpose, we're going to basically operate between cutoff and the ohmic region. So how do we guarantee that we're in the ohmic region? Well, I essentially have this curve here. But what we're going to focus on is we are going to essentially define a gate source on voltage. So the gate source threshold voltage is right here. That's whatever the minimum voltage is to start to get current to flow. You'll actually find that number for your experiment 35. The gate source on voltage is something the manufacturer is going to say, hey, you want to make sure this thing turns on? Apply this voltage to it. And whatever that voltage is, let's say it's 10 volts. Well, then that's the curve that I'm going to look at. And I can just say, well, there's your drain current. Here is your drain source voltage. And for whatever that number is, there's my curve. In addition to typically defining the gate source on voltage, the manufacturer is also going to say, you know what? I'm also going to define a drain current on. Now notice where that point is, right? This is where we're kind of testing a transistor and saying, hey, as long as the drain current is below that value, then I'm operating on this part of the curve. This is a straight line originating from 0 and coming up to there. This is the characteristic curve of a transistor. Period. So as long as that's the case, then we know that this transistor will be in the ohmic region. In addition to this, for these values, the manufacturer will also usually give you a RDS on resistance, which corresponds to that curve. For a lot of MOSFETs, this is a fairly low number. Few ohms sometimes even less. So all I have to do when I build my circuit here, I have some supply voltage, I have a drain resistor, and then I have my MOSFET. If I apply the gate source on voltage right here, and as long as the saturation drain current is less than ID on, right? As long as I'm less than this point, I'm guaranteed, because I'm on this curve, I've applied that voltage, I'm guaranteed to be in the ohmic region. That's simple. And once I know I'm in the ohmic region, this circuit can be redrawn. The difference between this and my JFET is what? Well, you're going to be given that RDS on in the table. You don't even have to calculate. course, keeping in mind, right, that drain saturation current is the amount of drain current that would result if this were shorted, which is nothing more than the drain supply voltage divided by the drain resistance. That's how I get into the ohmic region. So not a lot different than the JFET, except instead of it having to be a lot less than the saturation current, I just have to be less than IDR. I'm sorry, other way. IDSM. Instead of having to be a lot less than IDSS, I just have to be less than drain on current. Sense to everyone?
So we're just gonna stick or focus on the enhancement mode and not.
Yes.
Okay.
Yep. I'm done with the deletion mode. I kind of use the depletion mode to introduce the concept of how we can take that channel and deplete it, but also enhance it. And so if I start without a channel, then I only have the option to enhance it, to create the channel and create current. All right, so what we'll do, we're going to take a break here. So we're going to take 10 minutes. We'll come back at 1:45. All right. And when we come back, we're going to start to use this transistor in switching circuits. That's going to be the focus of what we're going to talk about using this for. All right, let's have some fun now with this transistor. So in some ways, this part is going to be a little bit of a review for you. We'll start simple. Before this transistor, let's say, for example, my drain resistance here is 1K. My drain supply voltage, 10 volts. And I'm using, I gotta find my data sheets here. Hold on. Wait, I lost my data sheet. There we go. So a small signal enhancement mode MOSFET, for example, my VN10LM. VN10LM. Actually, we'll change things a little bit here. So the VN10LM has a gate source threshold voltage of 2.5 volts, a gate source on voltage of 5 volts, and an RDS on of 7.5 ohms. So all I'm going to do, I'm just going to change this to 5. So VN, got it already. Yeah, VN10 LM. So RD on, RDS on, 7.5 ohms. Gate source on voltage, 5 volts. Gate source threshold voltage, about 2.5 volts. Those are characteristics right out of the table on page 481. All right. Make a little table here. Input voltage. Output voltage. I'm gonna put in 0. I'm gonna put in 5 volts. So when the gate, or when the input voltage is 0, the gate voltage is 0. What is the condition of this transistor? But below the gate source threshold voltage, this transistor is off. Acts like a very, very high resistance. And so my output voltage will be what? You want to take it to the extreme, what we're doing is saying this. It's an open. So the output voltage will basically be supply voltage, 5 volts. Now, if I make the input voltage 5 volts, which is the gate source on voltage. By the way, what is my saturation current here? 5 volts divided by 1K. So the saturation current is 5. Divide here. 5 divided by 1, 5 milliamps. I didn't include the ID on here. Let's see what that is, because I don't remember. ID on for this device is 200 milliamps. Way below that, no problem. Which means this transistor, when I have 5 volts applied to the gate, and my saturation current is way less than ID on, now we are in the ohmic region. And this transistor is acting like a resistance. How much resistance? 7.5 ohms. This is 1,000 ohms. Just like with our JFET, we have a voltage divider. So the output voltage here then would be 5 volts times 7.5 divided by the sum, which is 1,000 7.5. Math here real quick. So we got. There you go. $37 millivolts. About 37.2 millivolts. Not quite 0, but you know what? Close enough. What type of circuit do I have here? Gotta go back to digital. Low in, high out. High in, low out. What is this? You ought to switch. This is a digital logic circuit. What is it?
Inverter.
It is an inverter. Exactly. Okay. So I just built an inverter.
I think you make a mistake in that milliamp is millivolts.
Oh, thank you. Did I say amps or did I say volts? I don't remember now. I thought I said volts, but I wrote down amp. Thank you. Now, this is using passive load. That resistor is a passive load. The problem with this, I can build this transistor nice and small. And on a circuit, right, if I have a silicon, I can actually design into the silicon a resistor. Trouble is, it takes up a lot of space. So here's what we're going to do instead. Come back to my characteristic curves here. Drain current versus drain source voltage. And we'll draw a couple curves here, right? So let's say this is a gate source voltage of 3 volts. Here's 5 volts. Maybe this is 10 volts. I'm going to redesign this circuit so that instead of a resistor, I'm going to use another transistor. But the way I'm setting up this transistor, this is on where are we at here? This is on page 489. 489. Now notice what I did with the gate. The gate is also connected to the drain, which means for this device, the gate source voltage, so gate to source, and drain to source are the same. So we kind of 10 volts here, 5 volts here, 0 volts there. Then because the gate source and the drain source voltage are equal, we end up with point here, and then if this is just above the threshold, maybe a point here. Now, what that kind of creates is an operating characteristic that looks like this. Now, what's important about this? Well, when I'm operating this transistor as a switch, I'm operating back here. Remember, current divided by voltage is the inverse of resistance. So this is a very low resistance because the slope is very high. But here, the slope is lower. So this is a higher resistance, inversely proportional. So basically what happens is when I operate in this configuration, this transistor acts like a resistor. The exact amount of resistance just depends on the transistor itself. And as long as this resistance is a lot larger than my RDS on, right? That's what this is essentially here, RDS on. Then I will still get this dividing effect where when the transistor is off, I get the voltage here. And when this transistor is on, I'll get a lower voltage. And all I need to make this work is that low voltage coming out here is less than the gate source threshold voltage, so it does not turn on or activate another input. Still get that on and off, that digital result. So this device here, this is called an active load. Because it is still an active device, but I just have it configured to act like a resistor. And I still get that same switching characteristics. I still get the same voltage division. Let's say maybe this operates at, maybe as an effective resistance, it acts like 500 ohms. Well, fine. So now, because this went from 1,000 to 500, this is still 7.5 ohms. Ooh, I roughly doubled that voltage. Now it's all the way up to, 75 millivolts. Still very close to zero, still a lot less than the gate source threshold voltage. And the beauty of this is this active load is very, very small in physical size. Takes a certain amount of space to create a resistor and make the connections on silicon. It takes very little space to make a transistor. Now, that's about as far as the book goes with this. I just want to take it a little bit further.
Signal lower. That acts as a resistor also.
No, the lower MOSFET is still a switch. This is still acting like a switch. So when it's off, this acts like an open. I still see the drain voltage coming out. When it's on, it's still a voltage divider.
You replaced it.
So I replaced a
component with a MOSFET.
that is acting like a resistance. The lower transistor I didn't do anything with. That is still my switch. All right. So here's where I'm going to go just a little bit beyond what the book does. Because you all have the background to understand it. You know, let's just go ahead and use the same transistor. We'll put 5 volts in here. And I'll go ahead and build this with an active load. Now I'm going to take 2 transistors and put them in parallel. Now I have, I'll call it VA and VB. There's my output. I have 2 inputs now. So VA and VB. So if I have 2 inputs, how many different configurations or combinations do I have? VA can be 0 or 5. VB can be 0 or 5. 4. Right? 2 squared. Let's go back to digital. Right back. So I'm going to go ahead and go through those different combinations. So if both VA and VB are 0, what is the condition of both of those transistors? Both off. What's my output voltage going to be? 5 volts. Exactly. Now, VA is 0, VB is on. Now, this transistor is on, acting like a 7.5 ohm resistance. We'll go ahead and say that's acting like 500 ohms. So now I am dividing the voltage, right? I'm dividing that 5 volts. Calculator back here. So 5 times 7.5 divided by 507.5. That gives me 74 millivolts. Or in other words, pretty close to 0. If I just reverse that, so now B is 0 and VA is 5. Now this one's open and this is 7.5 and I get the same thing. Pretty close to 0. And if both of them are on, now I have 2 7.5 ohm resistors in parallel. Gives me what? Well, basically 3.75 divided by 507.5 3.75 times 5, or about 37.2 millivolts. In other words, once again, about 0. What have I just built? What type of logic gate is this? What's that? No.
And
What was that? What gate gives me a high output if and only if both inputs are low? Wow, how quickly I'll forget. It's only been a year. Come on.
Starts with that.
so
What's that?
it's-
Starts with that.
No. Okay. It's an OR gate.
Oh,
All right. I'll give you a second chance here. Same thing. Active load. But this time, I'm going to take my 2 transistors and put them in series. Same 4 combinations. Now, with both transistors off, no path for current flow. Output voltage, 5 volts. Now, I put 5 volts here. So this could turn on, but this transistor is still off. Reverse it. Same thing. Now, when both have 5 volts on, they become 2 7.5 ohm resistors in series, which is 15 ohms. So now we have an output voltage of 5 times 15 divided by 515. 5 times 15 divided by 515. Yeah, I would have hit 4. So about 146 millivolts. Or in other words, still about 0. What type of gate is this? That is an AND gate. What I have just done is built 3 different kinds of gates. And these are the only 3 gates that do any logic operation. Now, if I wanted a AND gate, what would you do? Take this NAND gate, you run it into an inverter. Now I have an AND gate. Put an inverter on the output of my NOR gate. What do I have? An OR gate. And I have just built those 5 logic gates using either 2, 3, or 5 transistors. And what can you do with those gates? Anything you want.
Build an XOR.
What's that?
XOR.
You can build an XOR using and ORs and inverters. Exactly, if you want that operation. This is the basis for what microcomputers, microprocessors, big logic configurations are built on. And the reason these are used, this type of device, is because by using active loads like that, I can make it really small. I can make these transistors, nanometers in size and fit millions of them on a chip.
It's started in the sixties.
Roughly, yeah. I mean, maybe more in the 70s. The transistor itself came around in the 50s. The ability to essentially create multiple devices on a single wafer developed a little bit later. Op amps have been around since I think the late 60s, early 70s. Microprocessors in force since a little before that. Yeah. All we've done is what? Over the last 4 or 5 decades. 6, whatever. All we've done is find ways of making these transistors smaller and smaller and smaller. And you can pack more of them in. And you can do more. All right. Still not perfect, though. We make this just a little bit better. Because one of the problems with this, as it sits right here, is that, remember that saturation current, right? So when I activate this gate, in this case, 5 volts divided by 500 ohms, I'm going to have 10 milliamps of current. This gate is activated, another 10 milliamps of current. Wow. Now granted, they're not going to both be activated, right? Because if this has 10 milliamps of current, that basically means the output is low. And if I have a low there, then the current here would be 0. But one of them is going to be on, and I'm drawing a whole bunch of current, creating power, heat, etc. So what can we do to make that a little better? Well, you do this. Note what I'm using here, right? So this is my N channel. This, though, P channel. And note that the source is connected up to the supply voltage. So what happens here, right? So if I take my input voltage and I take my output voltage, so we use the same transistor, okay? So when this is 0 volts, the gate to source voltage here is 0. This transistor is off. But here, 0 here on the gate, the source is 5 volts, just to use that example. So the gate source voltage up here is 0 minus 5, negative 5 volts, which for a P channel turns it on. So for our examples, that's about 7.5 ohms. This is, and just for the fun of making calculations, I've been assuming that that drain or the resistor acts like an open. Not really the case, especially when it gets really small. You might have some leakage and stuff. So let's just say it's, I don't know, 1 mega ohm. Just for fun. Well, now there's a path. So this is a low resistance, this is a high resistance. So if you actually calculate the output voltage here, you're basically going to have 5 volts times 1 mega ohm divided by 1 meg plus 7.5. Okay. In other words, we might as well say 5 volts. 4.9999 something. So 0 in gives me 5 volts out. Well, now, oh, and by the way, how much current's flowing? 5 volts divided by about 1 meg, 5 microamps.
Is that negative 5 out or 5?
What's that?
Is that negative 5 out for 0 in or negative?
No, it's positive 5
Oh,
because I'm dividing, right? This acts like a 7.5 ohm resistor. This acts like a 1 meg. We're just dividing 5. Now, when I put 5 volts in, this transistor is now on, acting like 7.5 ohms. The 5 volts here, the gate source voltage here is 5 minus 5. Oh, now the gate source voltage here is 0. That transistor is off, acting like a 1 mega ohm resistor. And now my output voltage becomes 5 volts times 7.5 ohms divided by 1 million 7.5 ohms. Or in other words, about roughly 20, do my math here. I'm sorry, about 32 microvolts, something like that. Close enough. In other words, 0. How much current is flowing? Well, I still have a 1 mega ohm resistance, so I still only have 5 microamps current. Minimal current draw. So this is referred to as complementary metal oxide semiconductor, or CMOS. So a CMOS type of configuration like this is basically going to draw the same minimal amount of current, whether the output is high or low. The only time you're going to have any current flow at all, right? If we think about what we think of a digital signal as just high or low, right? Well, in reality, there's a transition as it goes from high to low. There is some amount of what we call rise time, etc. And so during that very brief period of time here, when let's say we're at about 2.5 volts. But when I'm at about 2.5 volts here, then I'm just above the threshold here. 2.5 minus 5 is negative 2.5, just above the threshold there. So if we actually look at the current during that time frame here, you'd have 0, or 5 microamps, 5 microamps, 5 microamps, and just a little bit during that transition until the other transistor turns on.
That's the same abbreviation as the motherboard batteries on computers. So
Well, that's the technology that is used. Why? Why do we want to use CMOS technology? Minimal current draw, minimal power production. When you put millions of transistors on a chip, things are going to get a little hot if you're not careful.
the battery that is on the motherboard has the same abbreviation though.
Oh, yeah, the battery itself is not that, but a small battery with this technology will hold information, maintain information for a very, very long period of time because of that small current draw. So that's complementary MOS, minimal power consumption. Now, the last part of this chapter gets into power field effect transistors. All we're talking about with power field effect transistor is just a device that can handle higher currents or higher powers, right? They're put into larger structures that can dissipate that heat that is produced. It may also include an internal diode that is reverse biased during normal operation. And there are a few advantages about field effect transistors that are especially useful in power configuration. One of the problems that we had with transistors we bias a transistor, and just as a switch or whatever we're doing. We are operating on this type of curve, where we look at the, say, collector current versus the base emitter voltage, and we're operating here. We have some amount of collector current flowing, a certain collector emitter voltage. Now, if we're operating it as a switch, well, that collector emitter voltage is fairly small. But if we're in like an active region, we have this problem where as the temperature goes up, this curve shifts. So that if I am providing a fairly fixed base emitter voltage, the resulting collector current goes up. We call this thermal runaway. Well, because we don't have a forward bias PN junction in my MOSFET, I don't have this problem. In fact, what happens is as the temperature goes up, the resistance actually can go up. And so that'll actually help limit runaway, thermal runaway of any sort. In addition, when I put the field effect transistors in parallel, I don't have to worry about load hogging, right? Same idea. If I have two transistors here, and I'm trying to put them in parallel to do the same thing, well, if one starts to warm up, it's going to take more of its share of current and warm up even more. Field effect transistors don't have that problem. So I can easily run them in parallel if I need to increase the current capability. Another thing about field effect transistors, we are using a forward bias base emitter junction, which involves, those carriers coming together. Well, turning that off takes a little bit of time. The field effect transistor can respond more quickly, can turn off, because we're just taking away a channel completely. All right. So beyond that, and this is where, the setup for this and everything is going to be very similar, right? Whatever we have, if we have some load here, whatever that load resistance is, and I take my power MOSFET in here. This example, it needs to be able to handle at least 1 amp. And so I think there's a table of these guys. The bottom of page 495. where now we are looking at devices that have drain on currents in the amps, 2, 5, 12, 62 and a half. And the higher the current, the lower the RDS on. So you've got all those different configurations. So you give a homework problem where, figure that out. And it's the same thing, right? As long as you're in the ohmic region, maybe that's 1.95 ohms. All right. So now you got 10 volts divided by about 12. So you'll be able to handle about 0.833 amps of current. So some of the rest of the chapter is basically just some of the stuff we covered in power supplies, DC to DC conversion, things like that. Creating a bridge, the ability to drive this DC voltage. So a lot of this is just a little bit beyond what I want to get into here. At the very end, he does talk briefly about enhancement mode MOSFET amplifiers. All right. Configuration for that is going to be very similar to what we did with the JFET. We're not going to do any labs on that, so I'm not going to worry about that too much. He's added some other new stuff here that I'm not going to worry about as well. All right. I've covered what I want to cover with regard to MOSFETs. All right. So check something here. Oops. Okay. Question.
On that table that you were referring to, at the thermal runaway.
Yeah.
I see down there at the bottom device takes up the ID max of 125 amps.
Okay.
What are some applications for that? Are you talking like high voltage?
Not necessarily high voltage, but a lot of times power conversion. So that's the type of device. So remember in power supplies, how we took, DC to AC inverters. So when you're turning something on and off really fast, especially for like a true sine wave inverter, where you're turning on and off very fast, you're providing those current surges. That's the kind of thing you're looking at. So if I want to try and produce, where I've got amps of current flowing, then I need something that can handle that kind of current. But I still want to, but I'm still using it as a switching, right? Remember that was the whole thing about the true sine wave inverter in power supplies, was we were turning it on and off so fast that we could make it look like a sine wave. And you have inverters that can do that and provide, 10, 20, 50 amps of output. And that's where you're going to see those. Especially. All right. So I'm not going to start on chapter 14. So we're actually skipping chapter 13. 13 will be covered in industrial electronics offered next summer. So chapter 14 is where we're going to start next week. So feel free to look ahead on that. We're going to look at our common emitter amplifier in a whole new light. All right. That's what we're going to start looking at. But before we get into that, we are going to talk about different ways to look at measuring voltage, measuring current, decibel units, fun things like that. So feel free to review first part of chapter 14 in preparation for next week. Okay. Because we will dive into that pretty well. All right. So all right. So for homework, well, out of chapter 11, I do have 2 problems for you. 32 and 33. And then out of chapter 12, I got a lot for you. 9, 11, 15, 18. 19, 21, and 24. Seems like I'm missing something, but I have some lower numbers, but. Oh, no, oh yeah, the early one's on depletion mode, which I'm not. All right, for lab. They have experiment number 34. This is going to be just like Panera here. You're going to pick two. Okay. So in that lab, double check here. Ah,
I just caught up to what you said. I'm sorry.
yeah, yeah. So for experiment number 34, you can build an analog switch, a JFET chopper, a voltage variable resistance, or an AGC circuit. That's 4 different circuits. You just pick 2 of those. Okay. And then I'll just say appropriate questions. Or, if you build the chopper and there's a question on the chopper, then you answer that question. If it's a question on something you didn't do, you don't answer. All right. And so this is for JFET applications. Experiment number 35, that's your MOSFET. So for that one, you'll be doing steps 1 through 5. Which is mostly making measurements and creating that curve. And then you'll answer questions 1 and 2. And next week, quiz number 1. Quiz number 1 will cover JFETs. Biasing, ohmic region, active region, fun things like that. And like I said, we will dive hard into chapter 1. Questions? Okay. Rest of the time is yours. Work on that.
Can we get these?
Yeah, I've got them right behind me here. I'm going to go ahead and stop recording and I'll pass those.